So yes, so today is the last lecture. Yes, and it will consist of two parts. It would be, first of all, the material which we in generally was studying were more like theoretical and more basic. And today we will cover how real works which are happening with quantum computing looks like. We cannot give it as a full explanation, yes, but still it would highlight how it looks like. So the first, we ended the previous lecture with quantum noise, yes, and we told that all of it, if we speak on the language of density operators, then any operation which could happen, including noise, can be represented in the operator sum representative, so in such form. So it's linear in density operator, and it's parameterized by a family of operators, EK. Yes, and we have found this for applying of unitary gate. We have found it for measurement, but also we introduced that they could represent noise. Yes, and for example, we considered bit flip noise, where it was with high probability the state stays as it is, and with small probability 0 and 1 switches. Yes, and the same was for phase flip and others. I especially mentioned bit flip and phase flip because they would be important. The question is what we can deal with the fact that we have errors. Yes, in the end, whatever the quality of qubit we do, there will never be 100% quality. So we want somehow to help to have a mechanism for correction of error if it happens. Yes, and what is the way how, one of the ways how it is implemented, could be implemented for classical computers, if you have system, like if you have something which is in the state 0 or 1, and also we have idea that with a small probability it could spontaneously flip from 0 to 1 and vice versa, but with small probability. What we do, we make 3 copies of it. We have 0, 0, 0, and 1, 1, 1. Yes? And in that case, it's too much information, yes, because all of them are equal. But this allows us to recover. So because if one of them flips, yeah, so say we got 0, 1, 0, so it was 3, 0, and one of them flips. We count, we see 2 zeros and 1, 1, and we think it's much more probable that it was 0. So we correct it and say 3, 0. And this, how to say, we still cannot have a 0 probability of error, but the probability reduced, yes, because probability to flip 1 is small, then probability to flip 2 is even smaller. Yes, and the same idea comes to quantum work and to quantum bits. Yes, but now we don't have pure 0 or pure 1. We are not only in basis states, because to have just basis states is not enough to get a quantum advantage. Yes, so we want to consider mixed states as well. So superposition states as well. Yes, and then the first step in a quantum correction, quantum error correction, which we would do, is we would just copy this state. We kind of not copy, we extend it to 3 qubits. Yes, so we will start. So with this one, we take 2 additional qubits. Yes, And okay, this here we apply C naught to them, and so we get A 3 zeros plus B 3 ones. Yes, and this is analog of having a 3 copy of it. Yes, so we kind of record the word 0 in 3 times, and the word 1 3 times. After this, so the model in which we consider, yes, so the life is more complicated, yes, but the model which we consider, we assume that at this moment, after we created such a triple state, so we have a potentially bit flip error here, yes, so we apply this operation, which is bit flip noise, yes, so everywhere here we have operator sum representation. And we apply it to each qubit. Yes? So then, okay, now we have the state. And now it's an idea. So we would like to make a measurement. And we make a measurement not of some concrete qubit, but we make a measurement with specific basis. Yes, so we have this sequence of spaces. Yes, I will now introduce the family of spaces, and we would project with respect to this family. Yes, so first, it's the family which is spanned by 3 zeros and 3 ones, so two-dimensional space. Yes, and okay, this is a projection to the space. It has this form. Yes, so okay. This is to what corresponds this space. Any element of this space corresponds to the fact that none of those bit flips actually happened. Yes, so because then the system is a combination of all zeros plus all ones. Yes, so somewhere in this two-dimensional space, and in that case, nothing has happened. Yes, nothing with bit flip has happened. Yes, so it's invariant under this. Now, the second, so I call it P1. So I consider also two-dimensional space, but now corresponding to 1, 0, 0 and 0, 1, 1. It's also two-dimensional, and it corresponds to the case that this bit flip on the first qubit happened, and a bit flip to the second two qubits. So did I start the recording? I think I forgot.
Yes, you started.
Yeah, I started. Great. Yes. So then what's happening is that this is projection to the space where only the first error appears. So this is once again two-dimensional space. And P2 is the same space that which corresponds to the fact that second qubit flip, and the third and the last is then when the third qubit flip. So the good thing that, okay, this is two-dimensional, 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 so in total it's 8-dimensional, so this is a valid system of projections. And they are pairwise orthogonal, so we can make a measurement with respect to those projections. It's physically possible operation. And note that it happens the following. So if not more than one error appears, then we did not change the state. Yes, because if 0 error or 1 error appears, so we vote in one of those linear subspaces. So this measurement, in this case, didn't change the state. Yes, and in that case, you can say that, okay, if we got, so when we measure, we not only do projection, but we also read out to our classical world to which projection we have happened. So we know Did we get a result 0? And in that case, we will do nothing because we expect that no flips has happened. If we get 1, so we are on a P1, then we say that, okay, there was an error in the first qubit, so we need to flip it back. So we apply not to the first qubit. Yes, if we get 2, we apply not to the second qubit. If we get 3, we apply not to the third qubit. And in case, if there was not more than 1 bit flip here, then after applying this scheme, making this measurement, applying this correction step, we will also get a state which is 3 zeros plus 3 ones. So we corrected it back, yes, to the state where it was before. The same idea as for classical. But now we are in a superposition. We have a deal with superposition state. And yeah, so if we have only 1 bit flip, then it is correct. And if the probability of having bit flip was small enough, yes, it was very small, but this is what we should expect. Yes, we should have a good device. Yes, so it's not always flips, it's rarely flips. Then we need to see what is the probability that at least 2 of them would have a bit flip. And in fact, it would be proportional to Q squared. Yes. So we started with 1 qubit, which had a probability of error Q. And okay, now we have 3 qubits, which works as a single logical qubit. So we should think about this as a 1 qubit. But now it has an error proportional to Q squared. Yes. So summarizing, these 2 extra qubits, yes, for 1 logical qubit, we need to have 1 qubit plus 2 extra qubits. So instead of having 1 qubit, we need to have 3 qubits. Yeah, so okay, this is a big price. Yes, but we reduced an error from Q to Q squared. Yes, because yes, if 2-bit flip happens, so then we not correctly interpreted what is the result of measurement, we not correctly corrected, so we get something else, yes, in the system. But still, the probability that we have a correct result, so kind of nothing had applied in the end to the system is like probability of error is Q squared. Yes, so this is an improvement. Yes, but this is only for bit flip. What is happening for others? In fact, for others, we can do a similar idea. Yes, there would be slightly different scheme. So for phase flip, for example, you will need also to put, after you make such a similar state, you will also need to put Hadamard to make projections, to correct once again, and so on. Yes, but there are schemes for phase flip. Similar idea can be implemented for phase flips. And what is more interesting, yes, that you can combine several of those corrections. And here I combine the scheme for correction of phase flip and bit flip. So you start with psi, you kind of create a correction for phase flip, and for each of the qubits of phase flip, you do a correction scheme for bit flip. And so now you have 9 qubits instead of 1. And okay, it allows to correct phase flip, and it allows to correct bit flip. In fact, it happens that because we have operator sum representation. So, and it is linear with respect to density operator. Yes, so any operation including noise is linear with respect to density operator. It happens that if you correct finite number of noises, then you correct all noises. Because you have operator sum representation, so it's not on this slide, sorry. Yes, so let me show it somewhere. Yes, so yes, you have this form. Yes, and because rho is finite dimensional, so in any case you can represent it as a sum of finite number of steps, of finite number of those elements. And if you corrected each of them individually, you will correct the whole sum. I don't produce the proof of this, yes? And because, yes, we corrected bit flip, we corrected phase flip. In fact, the scheme is created in such a way that you will correct phase bit flip as well. Yes, and I don't ask for explanation. I will not give explanation of this. Yes, and it happens that bit flip, phase flip, and bit phase flip creates a basis. So every noise can be represented as a composition of phase flip noise, bit flip noise, and phase bit flip noise. Then it happens that such a scheme with a certain measurements behind could be considered, could cover any type of noise. Yes, and if error Q is small enough, so it would allow us, so the scheme would not work only if you have at least 2 errors. So you will move the probability of error from Q to Q squared. And here also comes a certain philosophical moment. The scheme would work only if Q is very, very small. Yes, because in fact, here in front of Q squared would be a certain multiplier, which basically related to number of qubits which happens, number of operations which you do here. Yes, and this coefficient should be like would be large. Yes, and then Q should be less than 1 over this coefficient. Yes, and up to now, I'm not sure that on practice it's happening. Yes, but in any case, there is another way because this is a concrete scheme. This doesn't depend on the type of the noise. So this is just one scheme. You can implement it on a hardware level. And if you implement it on a hardware level, then it could be much more precise. So kind of you construct either your lasers or quantum dots or these Microsoft surfaces, yes, whatever you do it in a such way that it would respect this scheme. Yes, and then you can make it better. Yes, so this is a philosophy. So this is called short correction code. But there exist surface correction codes. There are, I forgot the other names of correction codes. There are a lot of ideas behind how you can make this, yes? But this is a general idea. So kind of you create some scheme, yes, you kind of involve not only one qubit, but you involve more than one qubit. After this, you make a certain measurement, and this measurement is constructed in a such way that if there was no error in the system, no noise appears, that this measurement does do nothing. Yes, and okay, if you get this, nothing has happened, you're happy and do nothing. but if the result is different, you got some idea where was the error, and you correct it. So this is the idea of correction codes, and yeah, this is short correction code, the same short as the shorts algorithm. Yes, but in general, this is only an idea. And it always allows you with a certain price of qubits. So instead of 1, you get 9. Yes, so you multiply by 9 number of qubits. Yes, in your system, physical qubit. Yes, but this allows you to have a logical qubit with a smaller error. Yeah? So in this case, from Q to Q squared. Yes, and with a price of 8 qubits. Yeah, so this is what is possible. Yes, and theoretically, when we speak about the fact that we would have 1 million qubits, it could be very good, even that they are not perfectly precise. Yes, because from 1 million of good but not perfect qubits, we can create 1,000 of super very good qubits. Yes, and this is this gives us a lot of freedom. So it also allows you to build system in such way that you either use it all 1 million qubits, but with low precision, or you concentrate only on 1,000, but with a high precision. So this also becomes a flexibility. Yeah, so this is how it could work. Yes, and questions about correction, and this is what people are really doing. Yes, because now this is the main problem of the quantum industry is not number of qubits, it's their quality. And one of the main approaches is to create logical qubits. So when you consider several physical qubits, but they operate as a one logical qubit. Perguntas?
Sergey.
Yes.
So I missed a small part of the explanation. So is using the Adamar gates as you were using here, does this help with the phase flip specifically?
This is like we have a scheme, yes, which I show this scheme, yes, with such measurements, yes, and such correction, and this is for bit flip. Yes, if you do phase flip, it would look very similar, but you need to put Adamar here, yes, and phase flip here, and okay, after this, at some moment, we need to remove Adamar, yes, so to apply it again, yes, just to not touch the qubits, yes. But the correction part would looks like that you put Adamar here, yes, and do phase flip, because after Adamar, actually, phase flip becomes bit flip, so that they are somehow connected.
Okay, I see. So if there is a phase flip after the Adamar, then you can detect it in a way like that.
Kind of, it become kind of a phase flip, because you see in, like, if you come to the operator sum representation, yes, so we come to operator sum representation. In both cases, we have one gate which is identity, yes, and whatever operation you do, identity still is identity. Yes, you consider conjugation by Adamar. But you can somehow make certain operation to kind of to change this matrix to this one. Yes. So here the eigenvalues are 1 and -1. Okay, here it's plus minus I. You cannot change them so only by a change of only by conjugation, yes, but still we also have a second part. Yes, we also have a choice of measurement. Yes, so because for bit flip I omitted for phase flip I omitted here the part which is related with respect to which spaces we do measurement, what type is the correction, and so on. Yes, and in fact this is how it used. It's not correct that Adamar just moves bit flip to phase flip. Yes, because they're really not conjugated. But still, okay, I did some scheme for bit flip, why there is no modification of this scheme to create a phase flip. Yes, so that it exists. Yeah, so that's in the case. That's, yeah, I agree that it's not a perfect explanation. But here the main trick which I hide, yes, is the fact that, okay, this is a bit flip scheme, this is a phase flip scheme, and as soon as I cover those two, yes, and it happens because I attach it in this special way, it would also covers bit phase flip, yes, so the product, yes, error. It would comes automatically because I combine them properly, yes. Then, okay, it happens that this scheme covers 3 type of noise, yes, and if the scheme covers 3 type of noise, it happens that it covers all type of noises automatically because the operation was linear with respect to density operators, because operator sum representation can be decomposed into finite number of basic errors. Yes, and those basic errors could be as explained here. So this is the feature of quantum correction. So this is universal. So it's easy to create a scheme. It's possible to create a scheme for each particular type of error. But as soon as you created enough, or you covered enough of them, you covered all of them. And this is already kind of a certain type of magic. Yes, and this is what is happening here. Thank you for question. More questions? Okay. So let's proceed to the next part. I will make a break in the middle of this part. And this is solving of linear equations. And what means solving a linear equation? It means that if you have a matrix A and you have a vector B, then you want to find vector X such that AX equal to B. And you want to do this fast. And solving linear equations, if you can speed up solving linear equations, you can speed up a lot of things. Right? When you do numerical simulation of partial differential equations, they are all the time, most of the time is inside solving linear systems. If you speak about machine learning, yes, then most of the time you do operations with matrix. Yes, think about neural network and backpropagation. There are a lot of elements of solving this equation. So this is kind of a holy grail, yes, a philosophy. If you can solve linear equation, if you can speed up linear equation, you can speed up a lot of other algorithms, yes. And you work with quantum computers. It is always there is always a price with precision. Yes, but in particular in machine learning stuff, yes, it's sometimes it's more important to solve a question quickly, not to do this completely precise. Yes, and for example, in a lot of algorithms, you do stochastic gradient descent. Yes, when you pick up random input data and propagate it via your algorithm. Even this, the fact that you consider not all data, but you pick up some random part of it, it already creates you huge, not precision in gradient descent. Yes, so I don't know. Are you already familiar with the machine learning stuff, with neural networks, with gradient descent, or it is something new for you?
I'm somewhat familiar, like with the basic concepts at least.
Yeah, okay, basic concepts, yes. So then I will say, so a lot of time in back propagation is in solution of such questions, yes, and the actual algorithms which exist, yes, they also by themselves already have a lot of not precision, yes, inside the algorithm, yes, by default, yes, by construction. Yes, so sometimes it's okay to get solution not exact. Yes, and this is the holy grail, yes, of the numerical theory. And okay, in this lecture, I will not give the full algorithm. Yes, I will give a full algorithm, but not in full details. Yes, because it has too many. Yes, and the goal of this thing, so I don't expect that you kind of understand it completely. Yes, the goal of this part is to show how a real algorithm look like. Because kind of Grover and Shor, which we considered before, it was a certain coincidence. You were lucky that they exist. Yes, and in a lot of cases, it's good to have a specific algorithm for a specific problem. But what I would explain in this part, it's more like a machinery. Yes, kind of. You would do step-by-step simplification of a regional problem to a more, not more simple, but to more well adapted to quantum computer problem. We will see difficulties, we will resolve them. So it would be kind of more step-by-step business. Yes, it would contain much less, how to say, genius idea. Yes, it would be harder, it would be longer. And yes, I present not the latest version of this algorithm, so that there are improvements, yes, but still I want just to show how philosophically it looks like the step forward. Yes, I don't remember so the year when was introduced this algorithm, but it was something around 2015. Yes, so it's not infinite time ago. Yes, the Shor algorithm was introduced long time ago. The Grover algorithm was introduced long time. But this linear equation, okay, I didn't write. It's called HHL, where H, H, and L are the first letters of the authors of this algorithm, which I don't remember. Not good, yes, but still, this is the idea. And okay, let me make a formal description of what is the algorithm. Yes, so we have a matrix, and I assume, so this is matrix, capital N by capital N. And you should think about that capital N is huge, that you consider kind of, I don't know, matrix 1 million over 1 million. Yes, a really big one. Yes. And because for small one, you don't need quantum computer. And you assume that the matrix is so-called sparse. Yes, sparse means that a lot of elements of this matrix is are zeros. Typically, you assume that at each line of the matrix and at each column of the matrix, only a few elements are not zeros. And this is a typical situation how it appears in application. And it basically tells that, not everything is connected with everything. Yeah? So if you study numerical solution of partial differential equation, then usually it would be a huge matrix, 1 million over 1 million, but at each row there is only, I don't know, 6 non-zero elements. Yes, so this is what is happening. Yes, but they are somehow distributed. They have certain structure, but this becomes not simple matrix, yes, but still it is like this. And in which way we know this matrix, or in which way, how it is encoded in the quantum computer, first of all, I will tell later, more close to the lecture, to the end of the lecture. Second, philosophically, it's similar to Courant. Think about the matrix A in a proper form. Only non-zero elements, yes, are in your computer in the style that they are Courant. So, and we have a vector B, and so B has elements Bk, and because this is a vector of length of 1 million, so I assume that there is a state of the system, which is sum of Bkk, but of course I need to normalize. Yes, I need to make it of norm 1. Yes, so I have inside my system some qubits which are in this state. So I have matrix A stored, say, in the style of Courant, and vector B, which is just as it is. It's also actually style of Courant. Yes, and now I want to find vector X such that AX is equal to B. Yes, as good as I can. Yes, to find. And what we need to find, so I want to create a state. I want to create a state X such that like we have a X solution of this, then I write xkk. So once again, I have certain vector which represent the quantum state, and I need to normalize. Of course, X doesn't contain all information, yes, because it shows the direction of the solution, but not the norm of the solution. But okay, kind of this is the price which you pay for the fact that you are trying to solve in quantum computing. Yes, so the length of the vector you will deal separately. Yes. So this is the goal. And now let me do step by step. So the algorithm is not easier. First of all, I would like to say that I won't solve the system only for self-adjoint operators. Yes, so I want to assume that A is self-adjoint. But this is actually not a loss of any, information. So because we can consider such matrix B, if A was matrix n by n, B would be matrix 2n by 2n. Yes, and B would be self-adjoint. And I will show that if I would be able to solve linear equation for matrix B, then I would be able to solve a linear equation for matrix A. Indeed, So if I consider B multiplied by some vector xy, I will get A star y, A star ax. And then let me just solve a question where bxy equal to 0b. Yes, and in that case, I will get x, so such that ax is equal to b. So this is a solution. Of course, there should be some post-processing because also I got this 0 and I never get anything precise in quantum world. So I don't know, part of the solution would move here and it creates difficulties, but I omit them. This is kind of post-processing. Yes, so I have such a matrix AX equal to B. Yes, and it costs for me just one qubit, because if I want to consider vector which is 2 times longer, so which is the length 2 capital N, this is just 1 qubit more. Yeah, this is not twice number of qubits. It is just plus 1 qubit. So this is a small price. And for the small price, I can assume that my operator for which I solve linear equation is self-adjoint. And this would be very helpful in the solution. Yes. So any question for this part?
A star, what would it be?
A star is a conjugation of A. Yes. So
Oh, okay.
this is a matrix which is so it's we make a symmetry over the diagonal and put conjugation on each element. Yes, at this time. Yes, so this is that becomes a star is a conjugation. Yes, and it's easy to calculate, so it's straightforward. Yes, so we don't need to do complicated things to do this. Okay, so let me first present a philosophical idea how I would like to how I would like to solve the question. Yes, later I will show how to implement. And so assume that I already know eigenvalues and eigenvectors. Of course, I do not. Yes, but assume that I know. Yes, and know that eigenvalues are real because matrix is from now on it is self-adjoint. Yes, and in that case, I can represent my vector B in the sum of B beta j uj. So I represent it in my basis. Yes, so eigenvectors for basis. And this is why I need self-adjoint. Yes, because I want to have orthonormal basis matrix, or orthonormal basis of eigenvector for this matrix. This is why I need self-adjoint. And in that case, how would look like the solution? Yes, of the question AX equal to B. Yes, this would be just beta j divided by lambda j uj. Yes, because if I apply A to this vector, I would just multiply uj by, I will multiply each term by lambda j, so I will get B. Yes, that's a perfect story. And I put here proportional, yes, because this is not necessary a unit vector. Yes, so I would need to normalize. And now the idea is that I want to make a scheme which would not affect kind of the coefficient. I would like the scheme which would send the vector, the eigenvector uj to a vector 1 over lambda j uj. Yeah, so if I will find an operator which acts like this on eigenvectors, then I resolve the problem. But there is a problem, yeah? So any operation in quantum state, in quantum world, has to be unitary. Yes, and with unitary operation, I cannot send a vector of length 1, and uj is a vector of length 1, to a vector of other lengths. Yes, so it's just not possible. Yes. So the operator which will do like this is not unitary. But not unitary operations are not possible. So we need to be a bit creative, yes, with this story. And creativity in this case would mean that we know one operator which is not unitary, which we can do. This is measurement. So idea is that if we want to do this, we need to have somewhere a measurement. Because measurement is not necessarily a unitary operator. Yes, it's linear in density operators, but it's even not linear if we speak about states. Yes, about states as vector, about pure states. So this gives us a chance. We will use it. Yes. So I will now present the scheme without details, and we will go to the break. Yes. So let me do this. So first of all, A was my self-adjoint operator. Then I would like to introduce operator U. Okay, it is written here. But what is important that it is some real constants times I times A. This is the same expression which we saw on a very, I think, second lecture when I motivate why operators in quantum computer are unitary. Yes, I consider the Schrödinger equation, I considered energy operator as a self-adjoint operator, and I wrote a similar formula for the solution of a Schrödinger equation. So we consider exponent of I times our self-adjoint operator, and this becomes a unitary operator. Yes. Here, so let us look more carefully. So this is 2 pi I times A, and then I will multiply on some P. P would be a real parameter. I will explain its choice later. Yes, and U would be unitary operator, and it okay, we not really know, but okay, its eigenvalue would be 2 pi I, yes, lambda j, which was the eigenvalue of operator A times P. So this would be such. Yes, and I need to introduce operator U. I don't tell yet how to implement operator U. This would be the very last part of the today's lecture. Yes, but it would be possible to do this. And here we exactly would do the fact that A is sparse matrix. And the final scheme looks like the following. So we have 3 registers. One is input, one is clock, because we will use phase estimation. So this is the same clock as in phase estimation. And it would consist of T qubits. I will specify value of T later. And we will have one more qubit, it's called S qubit, yes. And it would play a role of qubit which we would entangle with the system and measure. Yes, so we need a source of nonlinearity. Yes, so this would be source of nonlinearity. And on a very simple explanation, so it works like this. So we make a phase estimation for operator U and vector B. So we put on a clock register certain information about lambda j. After this, we make rotation, yes, and this rotation, which depending on the value which would be here, we would put some value on 0 part. What is this rotation? I will explain on the next slide. After this, we will uncompute, so we will return back the eigenvalue, so we kind of return it back to the input and measure this state. And because it was entangled to everything, yes, it would just affect in a proper way the whole system. So it would affect the lambda j, the other things. Yes. So how it look like? Yes. We do the following. So, okay, mu k. What would be mu k? Yes, because we made phase estimation, so we will get here 2 to the power t times lambda kp. Yes, so we will get here in this in clock register those numbers, somehow superposition of them. Yes, and if it is a poor state, poor weighted state mu, this controlled rotation, yes, so this is rotation, would send mu 0 to this value, yes, and it has two elements. One would correspond to mu 1, so when we change this state, and here there would be some coefficient divided by lambda, yes, so that's if it was mu here, so constant divided by lambda there. And this is the source where we would divide by lambda. Yeah, so that we need to send, we want to send vector uj, yes, to something proportional to 1 over lambda j uj. We want to do this. And this 1 over lambda j would come in the end from here. Yes, and okay, because we put it here some value of constant divided by lambda, and for value 1, we still need to have a unitary vector, so it would automatically put the coefficient in front of mu 0 of this form. Oh, here it should be lambda. Oh, no, here it should be mu. I'm sorry, here it should be mu, because this is a mistake. Here it should be mu. Yes, but still this is constant over mu would generate me 1 over lambda j in front of uj. This is how it is. And the next step is to make a calculation, yes, how this scheme works, because now I introduced phase estimation. I consider this rotation, and we know inverse of phase estimation how it looks like. Yes, so then so next step is to make a calculation, but this let us do after the break. And there is one moment which I forgot to say. So I will not show in the lecture the implementation of this rotation. And the reason for this, okay, it exists. It's not so easy as one can think, but still it is a concrete scheme. So this is just some sequence of gates which does not depend on A. So this is just one scheme for all cases, yes? And because of this is, one-time job which you need to make, yes? And I would not just go into details, yes? And now, before we make a calculation why the scheme works, yes? Let us have a break. 5 minutes break. Yeah. And questions, of course. So, are you here? At least one person, please say, yes, I'm here.
Yes.
Yes, good. Because you see, this is a tradition that people who are in Zoom don't open a camera, yes? So then you have no idea if this person is here or not. Yes. In any case, it's just a black square on the screen with the name. Okay, so we have introduced all the elements. Let us do calculation how the system works. So the first we start with 0. I call it S register. Second 0 is the clock register, and B is the input state. Yes, so this is, I have 3 elements. And the first step is not I applying some gate, I just re-represent B in the form that this is sum of B beta J Uj. Yes, and because this is tensor product, so tensor product is linear, I can just write it in a such form. Yes, so this is sum of J, 0, S, 0 clock, Uj. After this, I do phase estimation. And the only thing which I would allow myself, yes, so phase estimation is looking for the value lambda j, which corresponds to the eigen value of uj, yes, which would be actually those elements. Yes, so kind of it's looking for mu k or for mu j, yes. And in this calculation, I would allow myself that, okay, let us assume that uj is an integer. Yes, we remember that if the eigenvalue is not, so eigenvalue has the form e2 pi I pi. Yes, this is the notation from the phase estimation, so that if pi is equal 0 dot pi 1 pi t exactly, then phase estimation will find phi 1, phi t exactly. But if it is just arbitrary long sequence of 0 and 1s, then it would just find it with a good approximation. But I will allow myself, because this is an approximate algorithm, that it would just find here exactly kind of the first digit of mu. Yeah, so it would find exactly mu. So to find exactly value 2 to the power t lambda kp. Yeah, so then, this is what is happening after phase estimation. It doesn't change the uj, yes, but for every uj, it changes the clock register from 0 to mu j. Yes, so this is clock register. So then this is like, in case if all mu j's are integer, this is just exact. If all mu j's are not integers, then this is approximate. Yes? So this is what is happening. So then I do rotation. Yes, and what rotation happens? Okay, it doesn't change mu j and uj, it changes only f register. And this is how it changes it. Yes? So it just replaces 0. Yeah? So here it is 0. It replaces it by superposition of 0 and 1 with a certain value of c. Yes, so that's c over mu j here and a proper value in front of 0. Yes. So what would happen? And after this, I uncompute, just make uncompute for phase estimation, so it just reverses. And because 0 uj was sent to mu j uj, so then reverse would say mu j uj to 0 uj. And so just kind of make it 0. So we are for a while we get here the value mu j. Yes, we apply this controlled rotation. We apply the rotation. So now some information about mu j is in the first qubit as well. And after this, we kind of uncompute back the intermediate state. Yeah? So we get things like this. And now let me open brackets. And I will open brackets, I mean, not completely, but just those. So instead of one sum, I will now have two sums. And in one of them would be coefficient beta j times the square root of 0, 0 uj. And on the second, it would be b beta j times c over mu j, 1, 0, 0 uj. Yes? And so this is two terms. And in this sum, all elements has the S register 0. And at each in this sum, all elements has S value 1. So when we measure, yes, what would happen when we measure this guy? Yes, and it happens that those coefficients determine the probability to get a 1, and those coefficients determine probability to get 0. And after measurement, we will do the following. So we have a price for making measurement, which is a nonlinear operator. Yes, that if we get 0, we think that we were just not lucky, and we think that okay, this time we were not able to solve the question. So let us run the things once again. Yes, so let us do the second attempt. Yes, so if we get result 0, it was just unsuccessful. But if we get result 1, then the state becomes proportional to this sum. Yes, and this sum is exactly what we wanted, because now this is okay, this coefficient beta j, and c divided by mu j is proportional to lambda k. So it becomes proportional to beta j divided by lambda j. Yeah, so this is, so this is exactly what we want. So if we get result 1, we say that, okay, we are successful. So let us continue. Yes, so we are done. Yeah, not let's continue, we are finished. Yes, so this is how it works. This is the price which we have to pay because we have implemented not unitary operation, and yes, solution of ax equal to b is not unitary operation unless a is unitary. Yes? So for any system, the solution cannot be implemented as a scheme as it is. Yes, so we need to introduce some nonlinearity, and one of the ways to introduce it is measurement, and we measure just one qubit, which introduce us enough non-unitarity. Yes, non-unitarity to solve the equation. And okay, now next I would explain what are hidden problems which we need to solve somehow. Do you have up to now any questions about how the principal scheme of this guy works? Perguntas, dúvidas? Okay, let's continue. So there are a lot of hidden questions which I didn't answer during the explanation. So first question, what number of qubits we should choose as a number of elements in block register? Because I mean, this is kind of important because we also need to have a low complexity of the algorithm. Yes, we want that we want that our algorithm is fast. Yes, and if you choose very large C, then the algorithm would be not fast. Yes. So, okay, in terms of precision, more higher value of T you have better, but in terms of performance and code of the length of the algorithm, smaller is the better. So appeared the question, what is the minimum under which we could get a reasonable result? And there is an answer to this question. So there is a certain threshold. So if you do less than this threshold, you will get a complete crap as an output. And if you are bigger than this value, so you just have more value of T, better the result. That's how it just slowly. The second, so I introduced this operator U, which was exponent of a self-adjoint operator. And when I explain this U, so yes, so U U was this matrix, yes, 2 pi I A P, yes. It was certain complex now. It was I times self-adjoint operator. And now it comes philosophical idea. So the quantum computer is based on quantum physics. Quantum physics, in any case, it's simulation of a Schrödinger equation. So in any case, it's computation of matrices of such form. Whatever you do, it is always like this. Yes? And this is exactly the form which you have here. So there should be a way. Yes, because I mean, the underlying mechanism, yes, is the same. Is Schrödinger equation. There should be a good way to calculate such matrices, to simulate such matrices. And yes, it is. The algorithm is called commutation of Hamiltonian. And by the way, it is useful algorithm not only for solving linear equations, it is useful in other cases as well. Yes, but why we should look for this algorithm, why we should expect that there is a good algorithm for this is because in the end, quantum computers are just simulation of such type of matrices, but okay, with a specific Hamiltonian, but we have our part. Yes. And third is implementation of this rotation, so which I told that I would skip. But so there was a parameter C there, yes, and parameter C I will explain how I choose because it has a meaning and it has a relation to performance of the algorithm in the end. So I will explain how to choose the number T. I will explain how to choose constant C, and I will show how to simulate Hamiltonian. So this is my next. So what is the complexity of algorithm? Yes, so what is the time during which it runs? So first of all, let me introduce notation. So I have a matrix, my matrix A has size capital N by capital N, and you should think about it as a 1 million over 1 million. At each row and at each column, not more than S elements are non-zero. Yes, so you have only 5 non-zero elements at each row. You have only 5 non-zero elements each column. And this value should be much, much smaller than n. You will see why. That's why we need. And yeah, so you should think about n is equal to 1 million and s is equal to 5. We would need one more element from the matrix, which is called condition number. This is ratio of the maximum eigenvalue over minimum eigenvalue. When you will start to work with numerical linear algebra, so not just write exact formulas on a blackboard, but to work with different operation with matrices on computer, even on classical, you will see, so it would be a very important number. Kind of, it tells in which range of scales you have to look on what is going on, yes? Because if their ratio is very large, then there are vectors who become very long, so you take a unit vector, yes, corresponding to lambda max. It becomes very long, but you have another unit vector, which after applying matrix becomes very small. So kind of you need to have inside matrix, you need to consider the big scales and small scales. It's very typical situation that effectivity of your algorithm, yes, is strongly depends on this value kappa condition number. So this is not something special for quantum computers. This is what happens with classical computers as well. And okay, you have epsilon, desired precision of the result. Yes, so because you want to get result with a pre-given precision, so you would work on this. Yes, and this is the answer. How this algorithm works, time for which algorithm works. I will explain on the next slide in a bit more details, but let us see the formula. It becomes proportional to logarithm n, and this is a huge speed up because your matrix was 1 million over 1 million, and it happens that 1 million is never a multiplier in the complexity. Yes, so this is a quantum advantage. Yes, because you kind of store 1 million numbers in logarithm of 1 million qubits, and it happens that this is coefficient of proportionality, not n by itself. Yes, be careful. So you in any case need to upload n into your quantum system. So upload, yes, if you do this in a Courant style, yes, will take n log n, yes, time. So this to upload the matrix would be longer than solving a question. This is a quantum computing paradox. Yes. The second multiplier is s squared, and we should not care about it much because this is, I told you, should think about this as a 5, 6, I mean, really finite number, really small number. The third thing is kappa squared. This is condition number squared. So I will, on the next slide, show from where this coefficient appears, why we need to have it. And those of you who studied classical algorithms for solving linear equations, so there are classical algorithms which are proportional to condition number, not to square of condition number. So this algorithm is extremely good in terms of size of number, of size of the matrix, but not very good in terms of condition number. So this is not the best asymptote. So it shows to you when this algorithm is useful. It is useful when your matrix is very large, but by some reason your condition number is small. It's a possible situation, yes, but you need to be careful. Should remember this. And okay, we have coefficient 1 over epsilon. This is for desired precision. Yes, and by the way, it's not logarithmic, yes, in epsilon, just proportion to it. We will see from where it comes as well. So, from where comes the time? Let us see what is the phase estimation. Yes, it's T, number of Hadamard gates, it's controlled U, which we run t times time for run Hamiltonian, plus t squared, this is time for quantum Fourier transform, and the same time for uncomputed, yes, because this is the relatively the same algorithm. So rotation, so you just trust me that it takes t squared time, so you, because I don't show the implementation, so here there is no other way, just trust me. Now it comes interesting moment. What is the probability of success? Yes, and if you remember, so there was this coefficient bj c over mu j, yes, times something, just times 1. Yes, so the probability that you get 1 is sum of squares of those numbers. And note that we cannot have c too large, because we need that c over mu j would be less than 1, because in another case we cannot implement a rotation, yes, because rotation, yes, was controlled rotation was acting like mu 0 goes to something mu 0 plus c over mu j mu 1. Yes, can you see here? 1, 2, 3, can you see here?
Yes.
Yes, okay, good, yes. So then this coefficient must be smaller than 1. So C must be smaller than any mu, okay, any mu, yes? And in that case, so C here should be less or equal than mu min. And it happens in that case that so that ratio C over mu j is less or equal than ratio of lambda min and lambda max, yes, because mu j C has to be mu min, yes, and mu min divided by mu j is less or equal than mu min divided by mu max, yes. So, and ratio of mu is the same as ratio of lambda. And this is equal to 1 over kappa squared. And so sum of bj squared is equal to 1 because this is a unit, because original state was a unit vector. So this is equal to 1 over kappa squared. So this is related to condition number. So before we get 1, before our algorithm end up with success, we need to run it kappa squared times. And this is where this multiplier comes. So just one single run doesn't depend on it doesn't depend on a condition number, but it happens that we need to run kappa squared times before we get a good answer. Yes, and as well, so we need to be able to encode into time, into clock register, the values between lambda min and lambda max. Yes, so, and the ratio between maximum and minimum is the ratio between 2 to the power t and 1. Yes, and in that case, we should be able to see that mu max over mu min less or equal than 2 to the power t. And in that case, the smallest t which we can take in order to algorithm work is actually logarithm. This is another price. But I mean, logarithm of kappa is much smaller than kappa squared. So in the end, it doesn't affect asymptotics. Yes, so this is how the smallest value of t which we can choose in order everything works. And we also need to choose p, yes, and oops, 2 pi, I don't need, it should be 1 over lambda max. 2 pi is over. So this is the idea. So exactly, I want to have it encoded in the clock register. Yes, and in fact, the smaller p beta, but we cannot make it smaller than 1 over lambda max. And this also tells that because we need to run the algorithm, yes, we need to choose p, we need to choose p, we need to know kappa and lambda max and the biggest eigenvalue approximately in advance. So we not just need to know the matrix A, we also need to have some information about its eigenvalue. So it becomes a complicated algorithm. Yes, it has a lot of pre-operation. Oops. And now let me come to Hamiltonian simulation. And Hamiltonian simulation has a certain idea behind. So we need to construct such an operator. Yes, as I thought. Yes, so I replace T by A because T is not the type. We have a number of qubits in a clock register, so I put A here. And idea is the following. So when it's easy to find exponent of a matrix, it's easy to find it when the matrix is diagonal, because then exponent of a matrix is just also diagonal matrix is elements, exponents of the elements of diagonal. So it's easy. So let us try to reduce calculation of any operation to operation of to exponent of diagonal. And for this, I want to do the following. So I represent H as a sum of matrices which are called diagonalizable. Diagonalizable means that at each column and each row, only one element is not zero. Yes? So let me draw. Yes, so I have matrix. Yes, very big matrix. Yes, but at each row I have only one element which is not zero. D1, D2, D3, D4, okay, one of them is on diagonal, D5, D6, D7, D8. Yes, for example, matrix like this. Oh, it's not in diagonal, yes? Only this one is on diagonal, but it's not necessary that we have this. But in that case, we can reorder rows and columns such that we will get a diagonal matrix. And reordering columns and rows is just a conjugacy. Yes, so it doesn't. It's not a big story. Yes, so it would be possible to calculate exponent of such matrix. Yes, and in that case, okay. Exactly to have this sum finite, I need that the matrix is space. Yes, and after this it comes mathematical statement, which kind of beyond quantum computer, it's in mathematics. It happens that exponent of I h1 plus h2a, remember, yes, okay, I don't know, do you remember, yes, but E of exponent of a plus b is not equal to exponent of a times exponent of b. Yes, it's not necessarily equal. They're equal only if a and b commutes. Yes, and we don't know two diagonalizable matrices are not necessary computes. Yes, but still it happens that the following statement is correct. So we have A, we choose R number of steps, and we first calculate exponent of H1 for the time A over R. After this, we do the same for H2. And now we have a block of two operations, and we repeat it R times. Yes, it happens that when the number of steps is large enough, then your result will be close to the result here. And this is from where the terms 1 over epsilon comes. So the main problem with precision, it comes from here. So that's the question, how large R you have to use. Yes, and in that case, if we have a sum, H1 plus HS, then we just do the same. So we do H1 A over R, H2 A over R, HS A over R. This becomes one block of operations, and we repeat it R times. Yes. So what I did on this slide, I reduced simulation of arbitrary self-adjoint H to diagonalizable matrices. Yes. And now on the next slide, I will show how to work with the diagonalizable matrix. Assume that we have an operator Q, which just sends K0 to KHKK. Yeah, so kind of this is the way how we represent the matrix. Yeah, so diagonalizable matrix, we consider Hy1, H22, H33, H44, H55, H66, H77, H88. Yeah, so we just have those elements here. Can you see this part? 1, 2, 3?
Yes.
Yes, great. Yes, and then appears a question how to calculate exponent of such diagonalizable matrix. And to this, it happens that it is extremely easy algorithm, so we just need to run proper phase shift. Yes, so on a first qubit phase alpha, on the second phase 2 alpha, on a third phase 4 alpha, and so on phase 2 times to the n minus 1 alpha. And if this qubit was in a poor state HKK, then the result would be that it would be in the state e to the power I HKK alpha HKK. Yes, because we would apply this element only if this one was 1, yes, because for 0 we multiply by 0. We apply this element only if this qubit was in state 1, but which contributes to the total value as 2, and so on. Yes, and so then the full scheme to calculate Hamiltonian would be the following. So we apply Q, we do this phase algorithm, and we apply Q minus 1, so uncompute. Yes, and in that case, if we had AK K0, it will go to AK HKK. Yes, this after phase algorithm, we multiply here by this coefficient. Yes, and after we uncompute, we get this coefficient preserved, but HKK becomes back 0. So we maps AKK to AK e to the power I HKK alpha, which is exactly what we need, which is the Hamiltonian. And so we need to combine all of this together, which I told, and I would not do this because there were a lot of steps, several of them I omitted. So it's quite a long story, but I still would like to have a conclusion. Yeah, so this is the principal scheme, which is based on phase estimation, and it's necessary to have measurement. And there is no way that you will construct such an algorithm without measurement because you are solving not unitary problem. And so if you solve not unitary problem, you must to construct somehow to get something not unitary. And the only way, at least in which I introduced, was the measure. Yes. So the algorithm not always works. Yes, it works only if you get result of measurement 1. So there is a chance that you are not successful. You do once again, you are not successful, and you repeat until you are successful. Yes, the total time is like this, and this asymptotics is very, very good in the size of the matrix, is very far from perfect in the terms of condition number, and it's actually not very good in terms of precision. Yeah? So this is a perfect algorithm if you want to solve very huge linear equations, very not precise. Then this is good. And the important part of algorithm was Hamiltonian simulation, and this is a good, it's important algorithm by itself. And important things that Hamiltonian simulation is responsible for 1/epsilon here, and the fact that we need to wait until we get 1 is responsible for multiplier kappa squared here. So all bad guys come. So in this asymptotic there are 2 bad guys, and for both of them I show what is the mechanism of them. Here I showed algorithm for arbitrary matrix. Of course, there are more specific matrices, and for them there are more specific algorithms. So please don't be surprised. You can, for example, type Wooding algorithm, yes, in Wikipedia or whatever, and you will find better asymptotics for some specific cases. Yes, but I mean, this is a active technology that consider a specific form of the matrix and construct for it a specific algorithm. Questions? So that's it. So yeah.
I don't think so.
Yeah. So thanks then for attending the course. Yes. So thank you very much. And now let me also show on a stop recording and show on a screen questions.